Okay, so what if I told you that one of the most famous pictures in all of science is just completely wrong?
Yeah, you know the one I'm talking about. That little nucleus in the middle with electrons just zipping around in these perfect little orbits. Kind of like planets around the sun. It's an awesome image, right? It's everywhere. But yeah, it's not even close to what an atom really looks like.
So, let's get into it. If that picture we all know is wrong, then what's right? Well, that's what we're going to do here. We're going to build up the modern picture of the atom from the inside out, and trust me, it's way weirder, and honestly, a lot more beautiful.
All right, so where do we begin? Let's start right at the center, the heart of the atom, where all the action is concentrated, the nucleus.
Okay, take a look at this table. The really interesting part here is that relative mass column. You've got your protons and neutrons, right? They each have a mass of, let's just say 1, and they're all packed super tight in the nucleus. But then, look at the electron. Its mass is tiny, almost 2,000 times smaller. So what does that tell you? It means pretty much all the weight, all the heft of an atom is crammed into that tiny little core.
And this just highlights the insane scale we're dealing with. Back in 1909, when Rutherford figured this out, the biggest shock was realizing that an atom is, well, it's mostly empty space. Seriously. To give you an idea, imagine a single grain of sand sitting in the middle of a giant football stadium. That grain of sand, that's the nucleus. The stadium, that's the whole atom. It's wild.
Okay, so we've got this super tiny, super dense nucleus. The next logical question for scientists was, so what are those feather-light electrons actually doing out there in all that emptiness? This kicked off the first big attempt to really map out what an atom looks like.
And you have to appreciate just how fast all of this was happening. It was just boom, boom, boom. In 1897, Thomson discovers the electron. Just 12 years later, Rutherford finds the nucleus. And then, get this, only 4 years after that, in 1913, this young guy, Niels Bohr, shows up with an idea that changes everything.
And his big idea, the game changer, was something called quantization. Basically, Bohr said that electrons can't just be anywhere they want. Nope, they're stuck on specific tracks or energy levels. You can think of them like shells. They could leap from one shell to another, but they could never be found in the space in between. This was a huge deal, a complete break from how physics worked up to that point.
And you know what? This model was a massive hit for one big reason. It finally explained something that had been puzzling scientists for ages. It explained why hydrogen atoms only spit out light at very specific colors, creating these sharp lines in its spectrum. Why? Because those lines were the exact energies released when an electron jumped from one of Bohr's special shells to another. It just worked.
But there was a fatal flaw, a really big one. According to all the rules of physics at the time, an electron whipping around in a circle should be constantly losing energy. It should be radiating it away, right? And that would mean it should spiral into the nucleus in a fraction of a second, causing the whole atom to just collapse. Bohr's model was great, but it had no answer for why this didn't happen. To solve that puzzle, things had to get even weirder.
And oh boy, did it get weirder. This brings us to the quantum revelation. It's time to say goodbye to those nice, neat orbits and say hello to the bizarre, fuzzy world of the electron cloud.
Okay, so this is the absolute cornerstone of quantum mechanics. So get ready. An electron isn't just a tiny ball. It's also a wave. At the same time, which means it doesn't follow a clean path at all. Instead, it kind of exists everywhere at once in this fuzzy cloud of probability. It's not an orbit, it's a 3D region of space where the electron is most likely to be.
So let's just compare these two ideas directly. The old Bohr model, it gave us a defined orbit. It gave us certainty. We knew where the little particle was supposed to be. The new quantum model, it gives us a probability cloud. It gives us uncertainty. We've traded knowing for sure for knowing the odds. We can't ever say the electron is right here. We can only point to a region and say it's probably in there somewhere.
And here's a really great way to get your head around this. Stop thinking of the electron as a tiny moon orbiting a planet. Instead, picture the electron as the entire atmosphere surrounding that planet. It's not a single point, it's a presence that's smeared out over a whole volume of space.
Okay, so if the electron is like an atmosphere, does that atmosphere have a shape? You bet it does. And this is where we get to the real architecture of the atom. We're talking about orbitals.
So what is an orbital?
Well, officially, it's a mathematical function, but a better way to think about it is as a 3D map of that probability cloud. It's the region in space where you have a really high chance, like a 90% chance of finding that electron if you were to look for it.
And the simplest map, the most basic shape, is the s orbital. It's just a perfect sphere. Every single energy level, every shell starts with one of these. It's the ground floor, the lowest energy state for that level.
But as you go up in energy, things start to get fancier. Once you get to the second energy level, you don't just get an s orbital, you also get 3 p orbitals. And these look totally different. They're shaped like dumbbells. And there are 3 of them, all pointing at right angles to each other, like an x, y, and z axis.
And it just keeps going. The next level up, you get 5 d orbitals, and some of those look like 4-leaf clovers. Go up again, and you get 7 f orbitals with even crazier shapes. But through all this complexity, there's one simple, really important rule. Each one of these individual shapes, the sphere, the dumbbell, the clover, can only hold 2 electrons, max.
So let's just run the numbers real quick. 1 s orbital, 2 electrons. 3 p orbitals, that's 6 electrons. 5 d orbitals, 10 electrons. And 7 f orbitals, 14 electrons. 2, 6, 10, 14. Remember those numbers. They are literally the magic numbers that build all of chemistry.
Okay, I know. We've been talking about spheres and dumbbells and probability clouds. It's all very abstract. You're probably thinking, why on earth does any of this matter? Well, get ready, because this next part is the grand payoff. This is where it all comes together. Bam! Take a look at this. That weird kind of clunky shape of the periodic table you had to memorize in school, it's not random at all. It is literally a map of these electron orbitals. Those first 2 columns, that's the s block. That big chunk on the right, the p block. The metals in the middle, the d block. And those 2 lonely rows at the bottom, the f block. And look at how wide they are. 2, 6, 10, and 14 columns wide, exactly matching the number of electrons those orbitals can hold. It's incredible. The whole periodic table is just built by filling up these orbitals, one by one, from the lowest energy to the highest. You just start at the beginning and follow the rules. This system is what tells us how electrons are arranged in every single element, and that arrangement dictates, well, all of chemistry.
So there you have it. We've thrown out that simple but wrong little solar system model, and we've replaced it with something much more complex, much weirder, but also, I think, much more elegant. This orbital gives us a beautiful, powerful map of where an electron probably is, which, of course, leaves us with one last mind-bending question at the very heart of it all. If that's where it probably is, where is it right now?